Okay. Hi guys, so this is the second lecture of time series. Last week we began by introducing what a time series was, and then we looked at some key properties of the time series, how to kind of process it, and then we also looked at a mini workshop where we looked at some Y-finance data and then learned how to sort of pre-process it for a machine learning model. So a bit of recap. What is a time series? It's simply a set of observations recorded over time. So it can be weekly, it can be monthly, yearly. This is an example of what a time series plot might look like. So as you can see, it goes up and down, and it is a continuous line and not like a scatter plot. And a key task in time series is forecasting. So you want to try and figure out and model past behavior, see things like seasonality, trends, and then use this information to predict better into the future. So this is an example of what a time series data frame might look like. Here we have some dates as our index, and then we have values. This can range from things like temperature, sales, and yeah. So we looked at things like seasonality, trends, cyclicity, and noise. So a trend is just like a long-term dependency over time. It can be increasing, it can be decreasing, or it can be stable. It doesn't always have to be a straight line or a linear trend. It can be polynomial, it can be exponential, it can also be non-parametric, and that's where there isn't a closed form solution. We also looked at cyclicity, which is basically repeating movements or oscillations over more than 1 year. So that's when it's going up and down, a bit like a sine or a cosine wave. And then we also looked at seasonality, and then this is consistent behavior within a year, and these are patterns that repeat regularly within a year. So it will also like form something like a sine or cosine waves. You have those peaks, you have those troughs, and like an example could be maybe sales. So during Christmas, during Valentine's, you might have like a spike in sales for certain gifts, and then during maybe lower periods, you'll have that kind of trough or that dip. We also looked at lag features. So for anyone who attended last week, what is a lag feature? So it's simply just kind of like when data is shifted behind, and it's used again as a form of feature engineering to capture patterns over time. We also looked at window features, and that's where you take a window of data, so let's say 3 data points, and then you calculate some statistic over it, like median, mean, and then this basically cleans up some of the noise that you might get in a time series data set. We also looked at extracting date and time features. So this is things like you might have, a date column that we looked at previously, and then you'll get kind of components like week, month, or the day to sort of understand relationships between, let's say, month and sales, or whatever the target variable is. We also looked at data pre-processing tips, so it's important to have regular intervals. We also looked at data leakage, and then we also looked at simple moving averages, which is again a bit similar to window features. It's basically you get a bunch of data points, and then you calculate an average over that. So time series decomposition. With a time series, you'll have that as sort of like your Y, and you can decompose that into different components, such as level, trend, seasonality, and noise. So defining a level, that's basically the average value in the series. And then a trend is the increasing or decreasing value that we saw before. Seasonality is those repeating short-term cycles in the series. And then noise, that's the random variation that we can't quite capture. So there are 2 different types of time series that we can model. We can do an additive model, or we could do a multiplicative model. Now, why do we care if it's additive or multiplicative? We want to be able to model the underlying components of a time series, like trend, seasonality, and noise. It makes us better at forecasting and predicting future values. So let's look at an example to understand this better. So if you look closely on the bottom hand left, we've got an additive model here and a multiplicative model here. If you were to, let's say, assume an additive model is actually multiplicative, then when you're trying to forecast, let's say, this data point, if you were to extend it over here, then you would severely overshoot what the actual estimate is. Same thing here. If you were to assume a multiplicative model is additive, then instead of sort of capturing this increasing trend or value, you would really, again, undershoot what the future forecasted data point is. So lags, I briefly mentioned this at the start. So it's basically the past values of a variable, and they're used to predict current or future values. So this is our original time series dataset. We've got our time index at 1, 2, and 3, and then we've got our corresponding values at 5, 10, and 15. When you do a lag, let's say at t-1, that's basically all shifted forwards. And then we're left with this nan value over here. Same thing here, a lag 2 just shifts everything forwards. And you can do this in Python via the shift function. So .shift1 would just mean a t-1 lag variable, and a shift 5 would just mean a t-5. In time series, it's really important to have a chronological order and have equidistant timestamps. So by equidistant, I mean the difference between each time index is consistent and the same. So pandas, we've done this quite a few times. Pandas is just like a data pre-processing library in Python. And then this snippet, this code snippet over here, is converting the date to a date time. Now, if a date is something like a string or a number, we won't be able to, let's say, do some feature engineering on that and extract things like month or day, etc. And this is like a really key function in time series analysis. And then we also use this dot sort values function to sort all our data or our time indexes chronologically. And then to check that our time intervals are consistent and there isn't sort of inconsistencies, we look at this .diff function and then look at .value count. And what we expect to find is like 1, 1, 1, 1, and that would correspond to, let's say, a difference of 1 between all our time indexes. If we saw something like 1, 2, 1, 1, 1, then we'd probably have to drop a row or two to make sure that things are consistent. So filling in missing values. Now, we've looked at filling in missing values in the previous Kaggle sessions, where with categorical data, you impute with mode, and with numerical data, you impute with mean. However, in time series, we often use linear interpolation. So that's basically where you have, let's say, your two data points here, and then you kind of look at what's in between. So you can see that's kind of in between. And then this line here is like a y equals mx plus v function. And then there's also this other variable called .ffill, and this basically stands for forward fill, and it uses the last value to fill in a nan. So let's say this is our previous data frame. We have 1, 2, nan, and then 4. After using a .fill function, this forward value is then propagated forward, and it allows us to actually capture this nan. Same thing here, this 5 is propagated forward. There's also a different function called bfill, and that's backwards filling. That then backwards propagates a value to the nan value. So let's look at that here. So as you can see, this 4 gets propagated backwards. Likewise, this 6 gets propagated backwards. But again, in time series, we normally use linear interpolation. Stationarity. So what is stationarity? This basically means when a dataset's mean and variance are constant and do not change over time. So this is what a stationary time series would look like. You can see that the mean is sort of consistent. It's not really increasing, it's not decreasing. And then you can also see the variance or maybe volatility. It's again kind of consistent. There aren't these sort of big peaks and troughs consistently. It's kind of like the same amount of variation consistently. Whereas here, this is non-stationary time series because we can see that our mean is slowly increasing. Likewise, this is again a non-time stationary time series because our variation as time goes on gets bigger and bigger and bigger. Now, how can you detect stationarity? You can do it visually, like I've shown you here, by plotting using matplotlib or Seaborn. But then there's also statistical tests or hypothesis tests that can give us a more robust estimate of whether our time series is stationary or not. Now, why do we care about stationarity? if we can better understand our time series data set and understand these sort of statistical components like stationarity, it allows us to better forecast in the future. And also it's a key assumption in many statistical time series models. So one way to understand if our time series is stationary or not is the Augmented Dickey-Fuller test. Now, this is a hypothesis test used to determine if a time series is stationary. And basically, it's H0 or null hypothesis is the series is non-stationary, and then the alternative hypothesis is the series is stationary. And we can do this via Python and we'll get a small p-value. And if this p-value is like really small, so I'm saying less than 0.05, then we can reject our null hypothesis and it's indicative that the data is stationary. Does anyone not know what a hypothesis test is? Okay, I think that's fine then. So this is an example of how you would implement the ADF test in Python. There's a key function here, import AD_fuller, and that's what you would use. So line 3 is simply importing the dataset using read_CSV. And then we can use the add_fuller function on our time series X, and then we have result. And there are different, result is a tuple, and the first element gives us the ADF statistic. The second index gives us our p-value, and then the fourth index gives us critical values. So we can look at the p-value here. That's 0.000052. So is that enough evidence to perhaps reject H0? And what does this suggest about the data? If we look previously, if we have a really small value where p is less than 0.05, yeah? This is stationary? Yeah. So yes, the data is stationary because this p-value here, 0.00052, is less than 0.05. So how can we actually fix this stationarity component? Well, the first thing is transformation, and that's basically when you're doing some sort of maths operation, like taking the logarithm or a square root on a time series. So here's an example. That's just np.log, that's just taking the logarithm, and then ts is our time series data set. A second way of transforming data so it's stationary is differencing. And this is basically when you compute the difference between consecutive observations. So let's say this is a data point, then you subtract the previous data point, and then this would be our first order difference. Extracting date and time features. So I touched on this last week and a little bit at the start, but to extract date and time features, we use this .dt.year or .month or .day, and this just allows us to extract different time components. Now, if you look at this diagram here, this is some data where the days of the week have been extracted, and then on the y-axis, we've got mean painting sales. Now, if we just originally had our data or that time series data, we wouldn't have been able to capture how on Friday, for example, we have the most sales, and on Sunday, we have the least sales. So that's kind of a real life example of why you might actually extract these date and time features. It basically allows us to spot patterns better, and then this allows us to forecast better. What else could you guys like perhaps think of another example of a component on the x-axis and kind of a variable on the y-axis that where extracting date and time features is useful? So here we've got days of the week. Often maybe sales are really high on a Friday because people have finished work and they want a painting. Another example I can think of is maybe months. So December, if you have all the months on the x-axis, December might have a really high sales because you have Boxing Day, you have Christmas, you have holidays. November might also be quite high because of Thanksgiving if you're in America. Is there maybe another example that anyone can think of? Yeah, you can say weather, you can say any. Exactly. So weather forecasting, you could have, let's say, the amount of rainfall. You could have months on the x-axis, where you've got January, February, March, April, May, and rainfall, I guess, in the UK is highest in April. So that would have like a really high bar chart there. So yeah, there's lots of different examples. And encoding cyclical features. So with time data, machine learning models incorrectly interpret months and dates. For example, December would be encoded as, let's say, a 12, and January could be encoded as a 1. And the machine learning model interprets that as being really, really far away and not similar at all. However, really, they're quite close, right? Because after December is January. Likewise, with o'clock, after 12 o'clock is 1 o'clock. So circular encoding is something that can be used to solve this. It preserves this circular continuity of time, and it enables models to learn recurring patterns naturally. So how can you do this in Python? You can use sine and cosine functions to interpret these months or hours on a unit circle instead of interpreting it as a linear number line. So you can use kind of this sine function or this cosine function and use the previous date time features you extracted and transform them in a way so you have kind of a cyclical version of time. I'm now going to talk about autocorrelation. Now, this simply measures the relationship between a variable's current value and all of its past values or lagged versions over time. So a positive autocorrelation would mean a high value today suggests a high value tomorrow, and a negative autocorrelation would mean a high value today suggests a low value tomorrow. So we've got this diagram over here. We've got kind of like a mid value. Well, this if there's positive autocorrelation, this suggests that this kind of highish value would have a higher value tomorrow. And this would then suggest there's another higher value the next day. Whereas with negative correlation, it's a lot more unstable or noisy. You've got kind of high, low, high, low, high, low. And to actually compute autocorrelation, we've got the autocorrelation function, or ACF. And this is a statistical method to quantify autocorrelation for a range of lags. So we've got this really ugly looking formula over here, and we can express it for each lag k. So we've got our time series, xt. We've got x bar, which is the mean of the time series. And then you would compute this. And whatever this returns, we can then interpret it. So if ACF equals 1, that means a perfect positive autocorrelation. And if ACF equals -1, that's perfect negative autocorrelation. Now, for people who have like a math background, does this remind you a little bit of anything? Where, let's say, I'm going to give a hint, it's called R, and it's used to measure something to do with correlation. Like, what is it called, or how would you interpret that value? You can have a guess, like, okay, so there's a Pearson correlation coefficient where R equals 1 would mean there's like a direct correlation or positive correlation. R equals 0 would mean no correlation, and R equals -1 is negative correlation. So it's quite similar to this. Okay, so there's lots of different time series models. On Wednesdays, Manu and the quant team have been looking at linear regression, and you can, use time series and encode that as a linear regression model and get pretty decent forecasts. And that would be for a multivariate time series. And that's basically when you have multiple features or columns that are dependent on that time index. Now, there's also univariate time series models, which is basically when you have your time series index and just one feature or column dependent on that index. And that's ARIMA and Profit. I'm not going to go into details too much because I have an activity at the end. But then I also want to talk about LGBM, so that's light gradient boosting model. And that's like a really powerful model that's used a lot in Kaggle, especially on big data sets, as it's quite good and it's very popular. Okay, so summary. We looked at time series decomposition, additive and multiplicative. We looked at lags. We also saw how to fill in missing values for a time series data set and how that differs from time series to just like a normal data set. Then we also looked at stationarity, which is when the statistical components like mean and variance are constant over time. We looked at the ADF test to sort of measure and detect stationarity. Then we extracted date and time features and encoded cyclical features as a feature engineering technique specific to time series. We also looked at autocorrelation and the ACF function. And then we quickly, briefly looked over some different types of time series models. Now, this is just a snapshot of time series stuff. There's a lot more to it. And if you go through these slides and try and explain each stuff to yourself in like layman terms, it's a lot easier to understand these topics because I have just like gone ham with a lot of information all at one go. Okay. So now we've got a Kahoot that I'm gonna host. Okay, 1, 2. That's 6. Okay. I'm gonna start now. Okay, so the keyword here is the best way. Often we do use linear interpolation. However, mean is another suitable value as well. Well done, Valeria. Like you can't see. Okay. So that was a bit of a trick. I said when a dataset's mean and variance do not change over time, so that's non-stationarity. Okay, you all got that right. I think someone dropped out. Okay, N is taking the lead. Okay, to allow the model to capture seasonal and repeating patterns better. Valeria's taken a spot. Oh, okay. What are lags? Pick the best answer. Again, the keyword here is best. Past values of a variable, and they're used to predict future and current values. Whereas t-1, t-2, t-3 is kind of like a relevant term, but it's not really like the best description here. And it also doesn't really say too much. Okay, next question. It's just between N and Valeria, this first place spot. Yeah, so ROC AUC is a metric or evaluation metric for classification models. You all got that right. Measures the relationship between a variable's current value and past values. What is a trend? So it's a long-term tendency over time. Consistent behavior in a time period probably makes more sense for like seasonality. So TOP stands for time of prediction. Okay. So when a model uses info that wouldn't have been available at time of prediction, I didn't go over this in too much detail. It's kind of like a carry-on question from last week. Okay, so it's extracting date and time features. So a window feature is like a new variable that's created by calculating statistics over a sliding window. Wait a minute. Yellow, new variables created by calculating the mean only. So the keyword here is mean only. That's quite difficult actually. Okay. Last question, make or break. Okay, so you can use all of these except ROC, AUC. That cannot be used to evaluate a time series model. And then this is for classification. Okay, leaderboard. Who's Jay? Well done. Valeria? Well done. First place. Who's that? Well done, Ed. Okay. This is. Oh my God. Okay. So we've also got another Kaggle competition, and this is an internal Kaggle competition. So only you guys and people who have the link in Queen Mary are able to actually submit to this. So it's a time series related data set. It's again very similar to the Kaggle competitions we've had in the past. You have your test, your train, and then there's also the leaderboard. It's empty right now. We've got code, so you can kind of do new notebook over here, and then press play or run to actually be able to get your data. Let's look at train. So I think the aim here is your target variable is sales. And I've also linked an old time series competition if you want to look at some examples of how to like actually model time series. So if you go to the leaderboard, this is forecasting mini course sales. You can go to, let's say, this guy. Well, actually, you can go to discussion code, say most votes. So this guy goes through like a step-by-step way of how you would implement time series models, or like how you would do feature engineering for this time series specific Kaggle competition. So here you've got importing the necessary libraries, you've got some summary statistics, and these are always really helpful because some of them are the winning competition. So you can kind of see the difference between, let's say, an average submission versus a winning one. Okay, and I think that's like the main task for today. But I've also got a mini research task. So the first step is to like get into pairs. And then I did touch upon some models very briefly, but I wanted you guys to sort of research a model. When you're doing Kaggle competitions, something that you'll find really common is that you're always sort of researching new models or new ways of doing feature engineering and kind of always improving. And I think this is a really good skill to quickly test, especially it's a Friday, 6 p.m. or 5 p.m. So maybe you're not in the mood to code, but I feel like this would be quite a fun task to do. So if you get into pairs, research a model, either ARIMA, exponential smoothing, profit, or linear regression, and you have 25 minutes to research this model. So what is it in layman terms? Really simply, why is it useful? Why do we care about it? What are the applications? What are some key components or maybe some maths behind it? Again, this should be really understandable to like the average person. You can assume like some basic data and machine learning knowledge. And then if you have enough time, the challenge would be a small code snippet or implementation. So you can really copy and paste this from any sort of website, but that would be like a challenge. And then hopefully we can, fingers crossed, we can present at the end in under 5 minutes. You can either use Google Slides and just have 1 or 2 slides, or you can speak about it using pen or paper. Some resources are DataCamp and Towards Data Science.